Now we're on apparently. Okay, all 5 of us here together. I don't know where the rest of us are. Maybe we're preparing for the hurricane. In any event, I'm still going to plod ahead and do what we've been doing. Before I go there, though, let me remind us that I have posted the final piece of test 2 is posted. It's worth 40 points, just like the other part of test 2. Again, I wasn't thrilled with what the scores were on the first part that I posted. I'm not blaming anybody in the class for that. I'm blaming myself. So I tried to pretty much make all the questions straight out of the lectures. You can find the answers if you look through them carefully. And there's 20 questions. I guess that means they're 2 points each. So please answer those 20 questions. I think I might want to say that I have it closing on Monday of, that would be November the 2nd, I'm guessing. I'm thinking pretty sure that it closes Monday, November 2nd at 11:30 p.m. So please make sure that you complete the remaining part of test 2. And then I'm going to put up some more things to do later the week after that for our 3rd test with regard to these things we've been talking about combining atoms together to make either compounds or molecules. Okay, so again, I get repetitive, and I know I do, and maybe some of you get tired of me being repetitive, but I try to reinforce the things that we've talked about several times over. I think it sticks a little better maybe if you hear me say it umpteen times instead of just once. There are essentially 2 different mechanisms for atoms to combine. The first is much like we have talked about for a few weeks now. That's when they transfer charge between each other. And literally, when neutral atoms transfer charge, one becomes positive, one becomes negative, and they stick together. And they are ionically bonding, we say. But it turns out that they don't do that in single units. They do it in multiple units and make compounds. Now, though, we're looking at the competing combination of atoms. And the competing combination of atoms is really, truly chemical bonding. It's more, I won't say it's more common, but it is really in the spirit of what a chemist will call a chemical bond. This truly is a chemical bond. This occurs when the elements which are combining have the same ability to pull electrons to them or give electrons up, or very similar ability to pull electrons to them or give electrons up. So since they have this similar desire to gain or lose electrons, one can't become a cation while the other becomes an anion. Nature doesn't work like that. Nature designs every atom of the same element remarkably the same. There's no deviations in the behavior of all atoms of the same element. So they all will then try to fight a tug of war over electrons that they can't win. So I guess in an exhausted state, they just surrender and say, I give up. Let's just each put our electron in the middle and we'll share these electrons. So this sharing of electrons is truly a chemical bond. In a single bond, each atom puts 1 electron into the share. And chemists draw a line connecting the 2 atoms, and that's representing a shared electron from each. In a double bond, each atom is going to put 2 electrons into the sharing zone. So there's a total of 4 electrons between the 2 atoms. And in a triple bond, each atom puts 3 electrons into the sharing pot. So there's a total of 6 electrons shared between 2 atoms. And so, of course, what we're going to learn later are there are different properties that result if atoms decide to singly bond, if atoms decide to doubly bond, or if atoms decide to triply bond. Now, we're not going to get into really deep aspects of the gore of what occurs, just the superficial surface general ideas that make for at least understanding the behavior of these kinds of connections. Now, another very important aspect of when they combine like this is I'm now going to be making molecules instead of compounds. Now, to your mom and them, saying molecule or compound might just be interchangeable words, that synonyms, if you like, if you're an English major, I guess, that you might call them synonyms for one another. But in chemistry, there's a distinct difference between a compound and a molecule. Molecules exist as individual entities. When you share electrons with another atom, you make units that are independent of the other units. Now, they're not completely independent, but they have their own structure. Their structure is independent of the structure of another unit. The compound, like NaCl, not only does one Na stick to one Cl, they stick to each other over and over and over and make big macroscopic chunks that you can see. Now, water is macroscopic, meaning I can see water, yes, but we also have to recognize water comes as individual water molecule units. That's why we can pour it so easily. That's why we can do the breaststroke through it so easily. Now, granted, you can tell when you're doing things like that it takes a good deal of effort to part the water molecules, but still, yet you can do so. You can part the water molecules, and what you're feeling as you're swimming through the water is you're breaking the intermolecular forces that are holding the cohesive macroscopic bulk sample of water together. You're disrupting temporarily those attractions as you move through it, but very quickly the polarity of the water molecules reestablishes those attractions for one another, and the water remains in the cohesive state that we call a liquid. Okay, now contrast that to, say, the air. The air, in many regards, is, well, first of all, it's a collection of molecules, individual entity units, but now the intermolecular force or attraction between individual units is so low that you can part air molecules without even recognizing that you're doing so. It takes no force, essentially, at all to walk through a gas. And it takes some force to walk through a liquid because you have to disrupt the local attractions that they're experiencing for one another. Solids, on the other hand, of course, you know, I'm strong and I can power through it, yes, but I have to exert significant force to disrupt the attractions that solids are exerting on each other in the connection that makes it solid. Now, the other thing to note, we'll go back to molecules. I will say molecules readily exist in the gas state. There are also many examples of molecules in the liquid state at room temperature. There are also many examples of solids that are molecules at room temperature as well. Now, once again, they're going to be easily parted solids that you can break apart relatively without applying ridiculous amounts of force again. But ionic compounds almost invariably are only solids. Now, crazy chemists have gone out and looked for weird behaving ionic liquids and things of that sort, and they have categorized and classified materials that they claim are ionic and claim are liquid. But generally speaking, for all intents and purposes, all ionic connecting or plus minus compound connecting materials are solids, because that's the nature of the massive amount of connection that they gain for one another. So we are currently talking about this concept of molecules, and we're going to focus our attention on the most important molecule former of all. And there is no doubt about what is the most important molecule former of all. That is carbon. Carbon is unlike any other element in nature, given its profound desire to connect to itself. Now, believe me, oxygen loves to connect to itself. Hydrogen loves to connect to itself. Hydrogen is the most abundant element in the universe, as a matter of fact, and invariably all the hydrogens in the universe are connected to other hydrogens. So they do love to, there's no doubt about it. Oxygen that we're breathing in and out through our lungs, of course, are oxygen atoms connected to other oxygen atoms. That's what we breathe into our lungs. So oxygen certainly loves to connect to itself as well. What distinguishes and differentiates carbon is not only does carbon bond to itself in a single bond to make one unit, it concatenates to itself over and over and over again, to the point that it gets macroscopic, to the point where, again, we can see it. There's so many connections between carbon atoms that you can see the carbon atoms. Like, for example, the plastic in my clock here. This is essentially entirely plastic. There's little chunks of metal here and there in it, but this plastic is almost entirely based in carbon. And any plastic that you use is based in carbon for certain. Now, there are, of course, other forms of carbon like carbon dioxide and carbon monoxide, which are gaseous forms of carbon because of the number of connections that they make with each other. So again, carbon has, just like oxygen and just like hydrogen, a desire to connect to itself. But the difference between hydrogen, oxygen, and carbon is that carbon will connect to itself not just in units of 2, but in units of 3, 4, 5, 6, 7, 8, 10, 10,000, 10 million, 10 billion, 10 trillion. It will just connect to itself over and over and over again. Oxygen, I guess we could force it to connect a couple of oxygens, more than 2, but generally speaking, no. Hydrogen, never. Hydrogen will only connect to one other hydrogen. So since carbon has this prolific ability to form molecules and bond by sharing electrons, not only with itself, but with other atoms as well, we're going to focus our study on molecules dealing with carbon-based molecules. We started doing that on Monday, and we introduced a class of molecules that are called hydrocarbons. These are carbon-based molecules that also include, as the name implies, hydrogen. So I'm going to have carbon and hydrogen alone in a hydrocarbon molecule, nothing else. So essentially gasoline is hydrocarbon. Now there are a smattering, I mean, come on, when you get even when you get a single gallon of gasoline, there are so many molecules in there. And as a matter of fact, of course, as well, the gas company adds what they call additives into the gasoline that make it contain things other than carbon and hydrogen. But there are the vast majority of every molecule in your gallon of gasoline is a carbon or a hydrogen. Now, of course, these are in molecular form, and very importantly, we can see them. We can see the gasoline. It's not invisible to us. Now compare that to the air. Air is molecules as well. We can't see the air. So what's the difference in the molecules that are in the gasoline liquid gallon that I can look at compared to the molecules in the air that I can't look at? Well, the difference is very simply that the spacing between the molecules in the air is incredibly large compared to the size of the molecules in the air. There's a lot of room between individual molecules. And of course, individual molecules are so small, you can't see them. So it's not until they get close enough packed into one another that we can finally begin to see them. And this occurs in sodium chloride when we shake it on our French fries. There's so many sodiums so close to so many other chlorines that they become macroscopic. And this also occurs in molecular forms, such as liquid glass of water or a gallon of gasoline. We can see them because the molecules in these molecular liquid states are so densely packed that we're looking not at one of them, we're looking at an almost incomprehensible number of them simultaneously so that we can finally discern its presence. Okay, so we began talking about connecting carbon in multiple units to itself. I named some prefixes that we're going to be using in the future, in our future exercises, so you might as well familiarize yourself with them. These prefixes indicate the number of carbons in connection in the chain. We're only going to name the first 12 because once you get more than 12, of course, chemists have names for them when there's more than 12, but we get the general picture of how we're going to do it if there are more than 12. So the names that we use to indicate the number of carbons in the chain are a little bit counterintuitive compared to the typical prefixes that the English language uses to indicate a certain number of things in a collection. Like very typically, when you have one thing in a connection, one unit in anything that we make we build an English word for, we would use the prefix mono. Mono is the prefix meaning one of those. But in organic chemistry, which is the chemistry based on carbon molecules, the preferred prefix for one carbon in the unit is meth. Now, the reason that meth is used is not from a systematic naming nomenclature chemistry point of view. It's from antiquity and from a common usage that grew from commercial use or common names given to materials before humans decide to systematize their approach to giving names. So meth means one. In the carbon chain hierarchy, for two, you might think we'd use di or bi. In words in the English language, di and bi typically are used when there's two things present. In the organic world, we use F. So meth is one, F is two. In the typical English language world, when we have three things, it's tri. In the organic world, it's prop, P-R-O-P on the end. And for four, it is typically something like tetra. We put that into a prefix and that tells us there's four things present in some collection. In organic chemistry, for whatever reason, again, historical reasons, they use bute, and it's spelled B-U-T like butt. So bute means four, prop means three, F means two, and meth means one in the so-called organic world. Now, once you get beyond that, though, they're really very typical. 5 is pent, 6 is hex, 7 is hept, 8 is oct, 9 is non, N-O-N, 10 is dec. Very familiar to probably the same terms that we would use when we're doing just basic English language. Okay, so we talked about then, okay, now we have the story of the carbon chain straight. Now we're going to talk about how do you actually go in there and connect the carbons in the chain. If the carbons all singly bond, and again, what does it mean to singly bond? That means each carbon puts one electron, antes up one into the card game. So I give one, you give one, and we pretend that we each get both of them. So we're sharing an electron from each carbon so that in total it thinks it has two when it only had to pay one. Okay, so anytime all the carbons singly bond, we attach not a prefix, I'm sorry, we attach a suffix or an ending to the name that tells us that. So the prefix will tell you how many carbons, the suffix will tell you how they're connected. And this is going to be a theme that runs through the naming of all the organic molecules. And it's really, after you get the basic premise of that, it's pretty simple. Okay, well, okay, I guess we shouldn't use the word simple. It's pretty straightforward. I prefer that word because I'm not going to say anything is simple. I think that's a little derogatory. So I'm going to say it's pretty straightforward to name, or from the name, to interpret how the carbons are connected and to interpret how many carbons are connected. Again, prefix tells you how many, suffix tells you how. So with that in mind, let's turn to my slides, and I'm going to go share my slides here. I'm hitting the share thing on my thing. I'm going to share my entire screen. You know, you should be used to it by now. I have to say these words while I'm doing it, just because that's what I have to do. So I'm going to click on this. So I'm saying the words. Then I'm going to click on this. So I'm saying the words. And so then I'm going to come down here and finally find my slides. And my slides are these ones. And we're now going to continue this theme where I will systematize the prefix, suffix, telling you how the molecules are connected. So I'm showing my slideshow from the current slide. Okay, so hopefully now we are popped up here. And I think what I'm going to do is I'm going to back up to the first slide here. And the first slide talks about methane. Now, let's get the theme. Meth means one carbon. Ane means all single bonds. And I didn't mention this part of the story, but this is an important part of the story. Carbon always, and this, you can take this to the bank. Carbon makes 4 bonds. Now, they might not all be single bonds, but carbon makes 4 bonds. So take that to the bank. As we go through the hierarchy of building these molecules, carbon makes 4 bonds. Now, the bonds, again, let's remind ourselves, because that's kind of important. The bond means it is sharing an electron. And if meth means there's 1 carbon in a hydrocarbon molecule, the remaining, I said it has to make 4 bonds. Everything else is a hydrogen. So you will notice that I'm connecting 4 hydrogens in a single bond, meaning a straight line connection to carbon. And this is the simplest possible hydrocarbon. And this is probably, at least in nature, the most commonly occurring hydrocarbon. It gets squeezed out of organic matter that is geologically packed into the earth. So there's lots of natural gas, we call this, which is packed into the earth and found in pockets of certain rock formations that have been squeezed together when you have these certain porous rocks like shale and other types of rock that have, of course, been squeezed together by seismic activity on the earth. This gas is very prevalent, distributed through pockets and even in the rock structure itself. Now, we've gotten so desperate to harvest these sorts of things that we undertake certain activities known commonly today as fracking, where we literally send fluids into the rock. And what sending the fluid through the rock is rather porous, kind of like sponge rock, if you like. Now, it's not, the pores in the rocks are very small, maybe hardly even visible to the human eye, but yet they exist. And the pores in these rocks are invariably filled with this methane gas. So what the so-called fracking process is, and there's not so much of it around here as there is in places that are more familiar coal countries like Pennsylvania. Like, actually, I know something about this because I'm actually a Pennsylvania guy originally. You might have thought, based on my accent, I'm not originally from here. I've lived here for 30 years or so, so I've been here long enough. But originally, I was a Pennsylvania coal mining son of many coal miners. But in any event, up in areas such as that, they have these shale type formations of porous rock, and they squirt liquid through the micro fiber, the micro state of the pores of this rock, and it squeezes the methane out and they catch it. That's fracking. Squeezing methane that has been trapped in porous rock out by injecting, I'm not sure if they elevate the temperature. I think they might. They inject rather warm or fairly warm water through the rock, and it squeezes the hydrogen out, or the methane out, and they capture it. And then they can do what they want with it. And this is economically feasible when the price of energy gets to certain levels. Okay, so enough of the fracking story. That's what they do when they capture natural gas from rock formations. Now, if I'm going to write the chemical formula of this, remember we talked a little bit about empirical formulas when we talked about ionic compounds. I will list the elements that are involved in the connection, and there's C's and H's. And since there are 4 H's in the connection, I put a subscript 4. Now for the C, there's only 1, but chemists never put a subscript of 1 in the chemical formula. So no subscript implies 1 carbon. Of course, the 4 implies 4 hydrogens. So the empirical formula of methane is CH4. Now then, just continuing that hierarchy to build ethane, and I take a methane and I pop off an H, then I take another methane and pop off its H, and then I just hook them together. So again, let's digest the name and what it says. F says 2. Ane says single bond. So the first thing you do is you put 2 carbons down and you connect them with a line. Now, carbons want 4 bonds. Carbons want 4 lines. So since I only used 1 line to connect carbon A to carbon B, carbon A needs 3 more lines. Carbon B needs 3 more lines. Since there's only 2 C's in the molecule, the other lines connect carbon to hydrogen. So this hydrocarbon, each carbon has 3 H's attached in single bonds, is what the line means. The other carbon has 3 hydrogens attached in single bonds. That's what the line means. And then the C's are attached to each other by a single bond, or otherwise the suffix would not be ANE. Anytime the suffix is ANE, the carbons are attached by a single line. Now, as a reminder, I said this before, but let's be clear. Hydrogen forms 1 single bond and 1 single bond only. Hydrogen can bond to itself with a single bond, but then that terminates the connections. Hydrogen cannot make more than 1 bond. So when you do these things, first look at the prefix, note how many carbons you need, then look at the suffix, it tells you how to connect the carbons, then finish the carbons off so that they have 4 connections. So this will be the structure of ethane. Now, if you're going to write the formula of this, chemists have done so in one of 2 ways. And which way you do so is really depends. That's the best I can say. Some you will equally as often see the chemical formula of ethane written in both of these forms. The first form just counts up all the atoms of C and puts a subscript to tell how many C's there are, then counts up all the atoms of H and puts a subscript to tell how many H's there are. So if you look at the picture, you should be able to translate that into the chemical formula. And I think later on my problems, there's going to be a picture of the molecule and it say, what's the chemical formula of this? And it will ask you for some choices of what it would be. And I mean, I think we can all count the C's and count the H's and know what the chemical formula of that particular molecule or any particular organic hydrocarbon molecule would be. The other competing way of writing the chemical formula tells you how individual carbons are connected to one another. So this is the competing way in which the name is done. Notice CH3 is also another means by which the formula of ethane is commonly expressed. Of course, CH3, if you put it into a single, or simplify it down, would be C2H6. But notice that you're getting a little bit of additional information in the second name compared to the first name. How? You're being told on C number 1, there's 3 H's. On C number 2, there's 3 H's. Now, generally speaking, most chemists can figure those sorts of things out anyways, but we'll see later in some examples where it does get a little trickier. So this second naming scheme gives you a little more indication about what's going on in each case for each C. Okay, now to continue this hierarchy, if I wanted to do a 3-carbon chain with all single bonds on the carbons, I would do propane. And as Hank Hill, one of my favorite cartoons of all time, as Hank Hill would say, propane and propane accessories. Can't help myself. Maybe some of you get it, some of you don't care. Okay, so propane would be prop, prefix, 3. Ane, suffix, single bond. So the first thing you do is you put 3 carbons in a straight line, connect them with a single line. Then the carbons always, and I repeat, always want 4 bonds. Each carbon wants 4 bonds. So what you do then in a hydrocarbon is you connect the remaining bonding positions with H's. H's terminate the chain. You can't go past the H to another carbon or to another H. H is only single bond once and they're done. Now, again, we could get into the reason why carbon always wants 4 bonds, the reason why hydrogen only wants always 1 bond. But again, if you want to answer riddles such as that, which of course we know the answer to, turn to a higher level of chemistry. For what we're doing here, we're just going over the basic premise of how to connect these hierarchies of molecules together. So, propane, 3 carbons, put a line between all 3 of them. Then let's fuzz it out with the H's. The end carbons need 3 H's. The center carbon, since it's connected to to a C on its left and a C on its right, it only needs 2 H's. So look very closely, every hydrogen has 1 line touching it. Every carbon has 4 lines touching it. And you basically have the general scheme of how to do these types of hydrocarbon molecules. Okay, so how would we write the formula? The compact formula puts all the C's with a suffix, subscript, all the H's with a subscript. There are 3 C's, and you will know 2, 4, 6, 8 H's present. So C3H8 is one way to write the chemical formula of propane. A competing way, which again, depending on who's doing the presenting and what they're trying to relay, would be writing it like this. The end on the left carbon has 3 H's. It is connected to the middle carbon, which has 2 H's, which is connected to the right end carbon, which has 3 H's. So sometimes people will write it in the form you see at the bottom of the screen, and it does give a little more information with regard to the connectivity. Okay, so let's just do a few more of these just to get the flavor. butane. As I said, but means four, ane means single bond. First thing to do, connect the four carbons with a line. The carbons are only singly bonding, so you put a line between them. And so this would be how I would do it. I would have the four carbons single connected. Each carbon still wants four connections. So the ND carbons all need, both need three H's to satisfy what they're going to do. The two central C's already are connected to two other C's, so they only need to connect two H's to them. So this will be the formula of butane. If I collect that up into an empirical formula, this idea of the methyl group and the ethyl group and the propyl group, let me save that for a later discussion. That's what we call when, if you have one connection that's meth connected, we'll look at how two are connected, that's an F connection. And if I look at how three are connected, that's a prop connection. Let's leave that out of the story for now. I'll return to this a little bit, just briefly, when we're talking about branching a little bit later. But let's talk, I didn't write the formulas here and I don't know why. Let's see if we can come up with the formulas that we would write for the empirical formula of these two. You count the C's and H's to make the empirical formula. C4H10 would be the empirical formula. Now, the more bigger formula that a little more information to it would be CH3, CH2, CH2, CH3. That is, of course, if added together, is still C4H10, but it tells you, again, a little bit more about individual carbons and their connectivity. Okay, just a couple more. One that your mom and them have heard the name of, octane. Octane, right there, I can tell you what's going to go on. Before we go any further with it, octane, oct means 8. So there's 8 carbons in a line. And then ane means single bond. So I'm going to put a line connecting all 8 of those carbons. Then the rest of the positions are hydrogens. How many? Well, each carbon, no matter what's going on, wants 4 connections. Each carbon on the end has only has 1 connection. It's connecting to the carbon inward from it. And the 6 middle carbons are connected doubly, 1 to each side, 1 to each side, 1 to each side. So the NDs always need 3 H's to finish them off. The middle ones need 2 H's to finish them off. So this then would be the picture of octane if I draw it out. And of course, octane is very familiar to us. It is synonymous, I won't say synonymous, but it's very commonly discussed when we look at gasoline, in particular, the rating of the power of the gasoline. I'm going to say a little more about that after we get through a little more of this nomenclature stuff. So I would prefer to tell the story of octane and what it means in gasoline. We'll save that story for until we get a little more practice with these naming things under our belt. So now that's the extent of my examples, but I think if I made hexane and I asked you which of these following molecules represents hexane, I think you could pick it out because it would have to have 6 carbons because hex is the prefix meaning 6. The carbons were all singly connected, and the remaining spots should have H's connected onto them. So you should be able to recognize those kinds of things just based simply on the name. So the organic chemists have chosen the naming scheme of their organic molecules a little different. Now, let's compare and contrast. Remember, in the ionic world, we had things like sodium chloride that told me straight up, first atom is sodium, and then the anion, because the ending is IDE, is chlorine. If I had beryllium fluoride, the cation was beryllium because it was listed first. Fluorine was the anion because it is given an ending change from INE to IDE. So in the ionic world, we had a strict nomenclature system that we followed. This is a very different nomenclature system in this organic molecule world. All these things are molecules. They exist in individual entities. Now, I will say octane, even though it's individual entities, is definitely going to be liquid. It is a major component, not a major, but a hefty component in a gasoline. It's by far and away not the major component of gasoline, but it's certainly present in gasoline, and it's certainly in the liquid state when it's present in gasoline. Now, the liquid state of gasoline, again, is there still individual units. I could put my hand in the gasoline and easily part all the molecules from one another. Now, they do have a high degree of affinity for one another. That's what puts them into the liquid state, yet they don't have so much affinity for one another that they make a rigid structure like a solid structure would be. Now, another thing, though, that I should point out, that it becomes readily apparent when you start dealing with these organic liquids. They stink! Organic liquids almost invariably are smelly stuff. And come on, just think about it a little bit. Fingernail polish remover, that's an organic liquid. Turpentine, paint, gasoline, all these organic liquids, stinky stuff. Now, what does it mean to a chemist to be stinky stuff? Now, here's the story behind what that means. These are liquids. You can pour the fingernail polish remover out, you can pour the paint out, you can pour the gasoline out. But the reason they stink is that they are not really sturdy liquids, meaning they escape really easily into the gas state. What a chemist would say is that these molecules have a high vapor pressure. They readily evaporate and make liquid. If you leave gasoline open, very quickly the gasoline will evaporate. Well, as a matter of fact, water will evaporate as well. Water individually doesn't have a detectable odor. So even though water is evaporating, you can't say, oh, I smell water, because of when the water is evaporating, it doesn't give you some sensation when it makes its way into your nostrils. Organic materials, invariably, when they make vapor form and get sucked into your nostrils, they lock into receptors in your system that you say, oh, I smell gas, or I smell fingernail polish remover, I smell paint. Okay, when you start to think about what that really implies, it's kind of not so cool, because you're literally ingesting the paint molecules. You're ingesting the fingernail polish remover molecules to actually do this detection of their presence. So in conclusion, what I'm getting at here is that molecules really aren't as sticky to one another as ionic compounds. Ionic compounds are what we call non-volatile. Non-volatile to a chemist means they don't exert vapor pressure. When you shake salt onto French fries, you don't get salt vapors coming off of the French fries. When you pour gasoline out of a can, you smell the gasoline because you get a lot of vapor phase or gas phase gasoline molecules escaping from the liquid state. So these liquid molecules are not very strongly associated liquid molecules, easily escaping into a vapor state. We call gasoline, not surprisingly, volatile. A volatile liquid makes vapor. And when your mom and them would think about volatile, they would probably mean burnable. Well, that's what actually burns. When you are burning gasoline, you are not burning the liquid gasoline. You are actually burning the vapors of the gasoline. And the same thing is true in your car engine. Your injectors make a very fine aerosol mist in the piston chambers. And it is this mist with highly, a lot of surface area connection to air that is actually burning inside the pistons of your car. So volatility to everyday English language usage kind of means combustible. That's what you would think. Volatility to a chemist means escapability from one phase into the gas phase. You can have volatile solids and volatile liquids. You have more volatile liquids than you have volatile solids, but there are volatile solids as well. They make vapors off of them. And the reason they make vapors off of them is they are not very well hooked together as individual units. The individual units aren't sticky to one another. Okay, so that's the story of these molecules. Oh, I forgot to mention, if I made the empirical formula, I would count up all the H's and C's and put subscripts. That would be C8H18. Or I could write it in the form, and I'm sorry to say, it's hiding under my stop showing button. So I'm not going to turn that off. If you look at the slides, what you would see is the two end C's have three H's, just like the picture shows. The middle six C's have two H's. So the end caps of these alkanes are always units of three H's attached to the end C's. The central C's on these alkane molecules are always two H's attached to each C. Okay, now as I mentioned, single bonding is not the only mechanism by which carbon readily attaches to itself. Carbon also likes to doubly bond to itself. Now, what does it mean for carbon to doubly bond? A bond is each carbon puts an electron into the share. That forms a single bond. A double bond means each carbon puts two electrons into the share, so that there are now 4 electrons total being shared by the two carbons. Now, once that occurs, each carbon still wants 4 bonds. That's its nature. It wants 4 more. It needs 4 more electrons. Going back to my analogy on Monday, to balance its washing machine. I talked about that washing machine story. I told the story of how and why they're motivated to combine it all. They're balancing their angular momentum. Carbons need 4 more electrons to balance their angular momentum. They're getting them shared with other atoms, making 4 single bonds. So in the alkene case, as opposed to the alkane case, the ENE ending is a tip-off that at least one of the carbons, and I will say that again, at least one of the carbons is doubly bonding. It could be more than one, but at least one carbon is doubly bonding to make an alkene. How do you tell how many carbons are doubly bonding? We're going to have to put some indications, as we will see how to do that in a shorthand, at a short time here. Okay, so alkenes, hydrocarbon chains, which one or more C's connected with double bonds, all remaining bonding sites occupied single bonds with H's. Okay, so what do we do for the name of them? You attach the ene ending, which indicates one or more carbons doubly bonding, and you use the prefix that we talked about previously, indicating the number of carbons in the chain. So remember, the prefixes started with meth, but there's no methene. Why? Because you need a double bond, and carbon can't doubly bond to hydrogen, okay? Carbon only. Single bonds to hydrogen. So there's not going to be a methene where carbon is doubly bonding to hydrogen. So let's just leave the meth prefix out. Okay? There's no methene. So we will start with F, where we have 2 carbons. That's hiding behind step number 3 that I have down there. Again, is hiding behind my start and stop button. We're going to expound upon what it says. It says how to write the empirical formula. So let's just take a look at what we do when we go forward here, and we'll demonstrate what step 3 is saying underneath the stop button. Okay, so F, as I said, ene is going to be the simplest carbon that has double bonds. Methane was the simplest carbon with single bonds. Ene is the simplest carbon with double bonds, because it takes 2 carbons to do it, because hydrogen can't take part in this double bonding stuff, because hydrogens always only want 1 more electron. Okay, now then, F means 2. So you take the 2 H's and you connect them together. Each H wants 2 more connections. I'm sorry, scratch that. Each C wants 2 more connections. Remember, each carbon wants 4 connections. The connections can be represented by the lines. The double bond means 2 lines, which means 4 dots, or 4 electrons. And so the carbons are seeking, really, if you look at it, 8 total electrons, 4 lines, each line representing 2 electrons. So if the bond has 2 dots each, we want 4 of those 2 dot bonds. You got to put 2 hydrogen bonds onto the carbons as well. Now let's contrast this between ethane and ethene. The picture for ethane would be a single line between the 2 carbons, and now to satisfy the carbon's needs, 3 H's attached to each carbon. Ethene has a double bond between the 2 carbons, and now because you've taken up some of the bonding of the carbons, you don't need as many H's. So essentially, from ethane to ethene, each carbon sheds an H, and the line that it used to have going to that H is now shared with the other C. That's all we're doing. We're going from CH3, CH3 to CH2, CH2. So the empirical formula of this will be written, those are just some words saying what I said. The chemical formula or empirical formula is C2H4, or if I put it underneath there, I might have put it under the stop sign, and I did. It's CH2, CH2, showing how each carbon is connected to each other. Okay, so let's do the next possible example. What if I was going to make propene? Prop means 3. Ene means double bond. Now, in the case of propene, we only want 1 double bond. Now, I should have, how do I know that? Well, I'm looking ahead. If we use more than 1 double bond, we tell you in the name. And we'll see that on an upcoming slide. When there's only a single ene, that means there's 1 double bond. So when I make propene, I will connect the 3 atoms together. There's 3 atoms with a single bond. Okay, so this would be the connection for propane. If I were making propane, that would be my connection. Instead, I'm going to put a double bond somewhere in here. Now, notice I'm double bonding the left carbon to the middle carbon. And that will make my propene, that's the starting point of my propene. Some of you might say, well, wait a minute, why is that fair? Why didn't you bond the middle carbon to the right carbon? Isn't that also equally likely? The answer is yes. I can either bond the left carbon to the central C or the right carbon to the central C. But what I will claim to you is that those are really the same thing, because the molecule in a solution or in a liquid state is just going to be rolling around in the liquid state. And when it's rolling around, notice the double bond sometimes will be facing to the left. When it's rolling some other times, the double bond will be facing to the right. So those two cases are the same case. One case really is just whether or not the double bond is sitting facing to the left or facing to the right. There's nothing different by putting the double bond from the middle to the right as there is from putting the double bond from the middle to the left. Now, that's not always the case, but in this particular case, there's really no difference in which way I orient the double bond. We'll see maybe on a couple slides down the road where that might make a difference in what's going on. Now, after I put the backbone of the molecule together, 3 C's, double bond, and then I'm still not done. Why? Because the C's are not satisfied in the state that they have. The left C has 2 connections to it. The middle C has 3 connections to it. The right C has only 1 connection to it. All C's, no matter where they are, want 4 connections. The left C only has 2. It needs 2 more. The middle C has 3. It needs 1 more. The right C has 1. It needs 3 more. So you should first recognize that that is what is left over in these cases. So that's what I'm going to put in those locations. I'm going to add H's to those connection points. The left C needs 2 H's. The middle C needs 1 H. The right C needs 3 H's. So when I'm done building my propene, this will be how it is done. Okay, now let's move to the next simplest, alkene. Remember, alkenes are carbon-hydrogen molecules that have double bonds in them. The next simplest one would be a 4-carbon chain. 4 carbons is bute. So the name of this is going to be butene, particularly if it has 1 double bond. Again, in a slide down the road or so, we'll talk about what happens when it has more than 1. But butene has 1 double bond. But now we will notice there is a unique problem that has to be dealt with. So let's go to the next slide. Let's look at butene. And what I'm stating here is we're going to encounter a problem. Now, what is the problem? Now I can put the double bond on the end. Now, what I would say is if I put the double bond on the other end, that's the same thing. Because I could just flip this over, and this double bond is equally the same on the left as it is connecting the 3rd C over to the 4th. So we'll say I'm now connecting the 1st C to the 2nd. I could have equally likely connected the 3rd to the 4th. But if I flipped the molecule with the 3rd to the 4th connected, it looks exactly the same as the 1st to the 2nd. So when these are rolling around in solution, connecting one of the C's at the end to the 1st C inward can be done one of 2 ways, we'll say. But this next picture is completely different. This picture that I'm showing now is a completely different way of connecting the C-C double bond. There's no way to flip this around and make it look like the top one. So these are 2 unique ways to connect the chain in butene. What I'm going to call a case like this is I'm going to call these isomers. Isomers turn out to be chemical compounds that have the same exact formula, but have different ways the atoms in them are connected. I think I might have mentioned isomers, and now thinking back, I know I did, when we were talking about Dalton's atomic theory. I had mentioned what an isomer is. Again, an isomer means you take the exact same number of atoms of each type, but you connect them in different ways, and those are isomers of one another. Now, it turns out isomers have slightly different properties. Usually not crazy different, but they still do have slightly different properties. Let me make a very clear example of where isomers play a uniquely important role. There is one form of THC, tetrahydrocannabinol, THC, the active ingredient in marijuana, where the atoms are connected in a certain way and it gets you high. If you take the same atoms, which are also present in this marijuana as well, but you connect them in a different way and you ingest those molecules, they are exactly the same atoms of the exact same proportion in the molecule, but the different connectivity of them in that molecule doesn't do anything for you. So one isomer of THC is psychoactive, or whatever you want to say it is. Other isomers of THC are not. So that's just one example of the drastic differences which can occur when you take the same atoms but combine and connect them in different competing ways. All right, so we now have to, in some way, differentiate the isomer formed when you make a double bonded carbon of the type in the top of this picture compared to when you make a double bonded carbon in the bottom of these two pictures. And here's what chemists have decided to do, and maybe you've seen this idea before, but it's logical. It's a very logical way of differentiating these two possibilities. I'm going to go on here and I'm going to take my chain and I'm going to number it. 1, 2, 3, 4. I'm going to start my numbering from the left. 1, 2, 3, 4. And well, actually, I'm going to start it more correctly. To be completely correct, I'm going to start it from the end closest to where the double bond begins. So 1, 2, 3, 4, I'm going to number it starting with 1 closest to the double bond at the end of the chain. Then a number is placed in the name of the compound to tell me that connection. Okay, so H's are put everywhere else that are needed to be placed. So once I put the chain like this, let's count up and decide how many H's to attach to each carbon. Remember, all carbons need 4 connections. Once the C connections have been established, place H's as the additional connections that the carbons desire. Carbon number 1 has 2 connections already. It wants 4. Carbon number 1 needs 2 H's attached to it. Carbon number 2 has 3 lines touching it. That means it has 3 bonds total. Actually, 1 double and 1 single. 3 bonds total on it already. It wants 1 more bond. Carbon number 3 has 2 carbons touching it, 2 bonds attached to it. It wants 4, 2 hydrogens needed. Carbon number 4, 1 bond touching it, needs 3 more, attach 3 hydrogens. So I'm going to do this, and once again, I apologize. Underneath my stop button, the left carbon has 2 hydrogens, the second carbon 1, the third carbon 2, the fourth carbon 3 hydrogens. And to tell the name of this this particular isomer, to make sure it's uniquely understood where the double bond is, I call this 1-butene, meaning in this case, the double bond starts at carbon 1. Now, let's compare that to the next case. Oh, I didn't show the next case. I don't know why I didn't. I'm sorry, I wish I had. 2-butene would be, let me back up, taking this bottom structure, the bottom structure that you see, where the carbon-carbon double bond is the middle C's connected, then you can see at the bottom that the carbon on the left needs 3 hydrogens. The second carbon over needs 1 hydrogen because it has 3 lines already. The third carbon over needs 1 hydrogen because it has 3 lines already. The fourth carbon in the line has 1 carbon touching it. It needs 3 hydrogens. So when you connect that together, you put 3 H's on the left carbon number 1. You put 1 H on carbon number 2, 1 H on carbon number 3, 3 H's on carbon number 4. Now, if you look at the formula for this, it will still be C4H8. 1-butene has a formula of C4H8. 2-butene has a formula of C4H8. Now, 1-butene, if I wrote it out in the other way of writing the name out, would be CH2, CH, CH2, CH3. That would be the lengthier way of writing out 1-butene, because the left carbon has 2 H's, the second carbon over 1, third carbon 2, fourth carbon 3. So it would be CH2, CH, CH2, CH3. Now 2-butene, which is based on the backbone shown at the bottom, still has chemical formula C4H8, has the same number of carbons, has the same number of hydrogens as 1-butene. But if I wrote it out in connectivity form, 2-butene would be written CH3, CH, CH, CH3. Now that is different than how 1-butene is written, which is CH2, CH, CH2, CH3. So these kind of different competing ways of writing the formula out give chemists a little bit more information about how the atoms are being connected. Okay, now let me go onward and just show you the possible isomers of hexene. Okay, hexene, first of all, before we show any pictures, let's just think about it a little bit. Hex means 6. I'm going to put 6 carbons in a chain. Ene means double bond. Now you can say, well, how many double bonds? Well, what I will tell you now is if there are more than one double bond, as we see upcoming, you will be a tip-off. There's going to be a tip-off in the name. But for hexene, since it has that ene ending, 1 double bond is present. But now there are, it turns out, as we will see in the pictures, 3 unique ways of putting that double bond so that it makes unique isomers. Here's what they would be. Like that, or like that. Okay, so the first one I'm going to call 1-hexene. First, note 6 carbons in a line. Ene says double bond a carbon to another carbon. Since it says 1-hexene, put the double bond on carbon number 1. Okay, then, once the double bond is put on carbon number 1, each carbon still wants 4 bonds. Connect to those carbons the H's that it needs, very simply. And then if you have 2-hexene, move the double bond over to starting at the second carbon. So let's notice the difference between 1-hexene, 2-hexene. The carbon double bond starts at carbon number 1, and 2-hexene, the carbon double bond starts at carbon number 2. Now then I'm just going to connect the H's as they should be so that each C has 4 connections to it. Then below at the very bottom, I show 3-hexene. 3-hexene has 1 double bond, but it starts at carbon location 3. And I put my double bond at that location, then count up how many H's are needed and put them in the locations so that each carbon has 4 connections to it, whether it has a double bond or a single bond. Okay, now the next thing I want to point out, each of these has the overall formula C6H12. Count up everything you see. Each of them would be written C6H12. 1 hexene is C6H12, 2 hexene is C6H12, 3 hexene is C6H12. Another difference, though, is you can tell the difference between them if we went to the individual carbon formula style. 1 hexene would be CH2, CH, CH2, 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 CH3. So I just state each individual carbon and how it is connected to other H's, and literally how it's connected to other C's as well, based on where it sits in that order. 2 hexene would be CH3, CH, CH, CH2, CH2, CH3. That's how I would write its formula if I was doing that named out scheme. And then the bottom isomer of hexane. Again, it is still C6H12, but that one would be CH3, CH2, CH, CH, CH2, CH3, showing its individual connectivities. Okay, I think what we've had is enough stuff for today. I think what I'm going to do is stop presenting, and we'll adjourn our time together until next week. And remember, please go out and do the assignment, or the part 3 of test 2. It is due on Monday at 11:30. 20 questions that have to do with the things we talked about with electricity earlier. So please do that. Okay, so next week, be safe from the hurricane. Peace out.